So let us now understand what is novel view synthesis. What do we mean by novel view synthesis? Let us understand that. So basically, if I talk about novel view synthesis, so it is made up of three words: novel, view, and synthesis. So the meaning of novel means unique, so something unique. View means scene, or an image, you can say, frame, image. And synthesis means generating. So novel view synthesis is the task of generating images of a scene from camera viewpoints that were never originally captured. So the idea is that novel view synthesis is a task wherein we will be generating some novel images, like the images which does not exist in reality, rather we are synthesizing it. So it is a task of generating images of a scene from camera viewpoints that were never originally captured. So novel view synthesis is the computer vision task of generating photorealistic images of a 3D scene from camera viewpoints that were not present in the original input data. So in novel view synthesis, we make use of sparse set of calibrated images. So the meaning of it is, like, let us suppose we are capturing an object from different camera angles. So let us suppose I have 20 samples of an object from different camera angles. So that I can call it like the sparse set of calibrated images. Calibrated images because they were captured with a direction in mind at certain angles. So, and also I have known camera poses. I also have the data, like, okay, this image is captured from this angle. Okay, this image so input will contain two things, the image and the camera pose. Okay, this image, it is captured from this pose, like the front, from the back, from the side, like that. So in novel view synthesis, what we do, we make use of this information, like we will make use of the information that, okay, if this is the camera pose, this is the scene, it is how the scene looks like. And with this information, we generate images of a scene from new camera viewpoints. Then I'll say that, okay, let us suppose I have information that this is the image, like this object looks like this from the front view, it looks like this from the back view, rear view. Then novel view synthesis will generate images like how it will look from the side view. That's the idea. So the output of novel view synthesis, it is the photorealistic renderings from arbitrary viewpoints. So novel view synthesis means making use of the input, that is the set of calibrated images along with the known camera poses. With that information, we will be generating, we call it like the photorealistic rendering. That is the novel view synthesis from arbitrary viewpoints. So essentially, it uses a sparse set of 2D photographs to mathematically hallucinate what the scene looks like from a new angle, filling in missing geometric and lightning information. That is very important because uh, it will like generate uh, images from the new angle, and it will fill the missing geometry and lighting information, because which was missing in the input data, because input, it has information about certain camera poses, but with novel view synthesis we can synthesize images at some more poses, and we can very clearly feel the application of this technique, like in cinematography, like in filmmaking. It can be very powerful. Like let us suppose, like we captured a scene from few angles. Now with this technique we can render, we can basically do the photorealistic rendering from different camera angles. Okay, now next very important question is why NVS is hard, the problem of novel view synthesis. Now this technique, it's not easy. And what are the challenges, let us see. So the fundamental goal of novel view synthesis is to bridge the gap between discrete 2D samples and a continuous 3D experience. See, the idea is that why we will be concerned about novel view synthesis. The main goal of novel view synthesis is that we have some frames. We call it like the discrete 2D samples uh, of images. We can call it frames. Now, using that, we have to make a scene in 3D which should be continuous. So using the discrete 2D samples, we have to build a continuous 3D experience using novel view synthesis. That's the main goal. So in novel view synthesis, the input is a limited collection of images with known camera positions. And the output will be a continuous video or interactive rendering, allowing the user to fly through the scene freely. So the input will be a discrete set and the output will be a continuous set. And from this, we can feel the challenge. Now the challenge in front of us will be missing geometry information. Because see, the input, it will not contain all the geometry information. It will contain only images with certain camera poses. So, and here we have to synthesize the images in new arbitrary poses. And missing geometry information is a very big problem. Because let us suppose I have an object, if I don't know how it looks from the back, then it's nearly impossible to generate exactly the photorealistic image of an object from the rear, because I should have some geometry information. So that is very common. So missing geometry information is a very big challenge in novel view synthesis. Occlusions not visible in training images. Like if you take a photo of the front of a statue, the back is completely unknown. The artificial intelligence, it must plausibly guess the geometry of hidden areas. So occlusions is a challenge in novel view synthesis. Light variations is a challenge. Why it is a challenge? Because see, the idea is that now we are not at all aware of the lightening of the environment from where the input was captured. Because when we collected the input, we captured the images from certain camera poses. So from there though we can get the information about the light. But if I want to generate, I want to synthesize the image in a new camera angle, from a new camera angle, since I am not aware of the lightning condition of the environment, so whatever I will generate, it might not be realistic. So lightning variations is a very big challenge in novel view synthesis. View dependent effects like reflections, specularity, these are challenges, because materials like glass, water, or brushed metal, they look different from every angle, because they shine, they have some reflection. A static 3D mesh cannot capture how light dances around a surface as the camera moves. So that is a very big challenge, that because since we want to create a continuous 3D experience, so the camera will be moving. So for every camera angle, I should have a photorealistic experience. That will be difficult because of like materials like glass, water, they reflect light and it looks different from different angles. Sparse data. Yeah, so sparse data. So the idea is that na, the data is like a subset of infinite reality. So the data, if we talk about which we will be using as input, it will be just a very limited subset of the infinite possibilities. So from that sparse data, we have to generate infinite possible 3D interpretations. That's very difficult. So now it's very clear that, okay, novel view synthesis, the challenges, the problem of novel view synthesis. So the main problem, like the key insight which we can take away is that the problem of novel view synthesis is ill posed. Like many 3D scenes can produce the same 2D images. Okay, now what it means, see, since the data is sparse, since we have sparse data and we have to like simulate the 3D experience. from the sparse collection of data. We have to simulate the 3D experience. So it is like very difficult. We can hallucinate. So many 3D scenes can produce the same 2D images. Because of the limited input data, we might end up producing the same, we might end up synthesizing the same photorealistic images across. So that's the main problem. Okay, now let us look at the applications of novel view synthesis. So see, novel view synthesis, it has got applications in virtual reality scene reconstruction. Because in virtual reality, we have to synthesize scenes in real time. So novel view synthesis can be very effective. Film production and virtual cinematography. So this we already saw that, okay, if we talk about like directors can film a scene with sparse cameras and then reshoot it from any angle in post production. This we already saw. Cultural heritage digitization, wherein so the idea is that we can capture some images of some cultural heritage from different angles, and with the technique of novel view synthesis we can generate a continuous realistic experience, 3D experience of that heritage. Because novel view synthesis, it will generate all the missing links, missing like all the like it will generate images, it will synthesize images from all the known camera poses. So that's the idea. Autonomous driving simulation, it can be very effective in simulations. Robotics perception, so the idea is that robots, they can perceive their environment, like using, like the idea is that using the some discrete set of input images, they can we can generate uh like a realistic 3D experience. So robots, they can act, they will get an idea about their 3D world, and they can act accordingly, which can be very powerful. Telepresence systems, so this is like a digital twin wherein uh, like like very realistic 3D presence of a person can be created. So that's a telepresence system. So that is basically creating holographic avatars for VR meetings from webcam feeds. Now, if we talk about novel view synthesis, okay, so now we see, we saw that, okay, what is novel view synthesis, what exactly it is, the technique that we got to know. We also looked into the challenges, the problem of novel view synthesis. We looked into the application of novel view synthesis. Now, the very big question, how exactly we can achieve, how exactly we can do novel view synthesis? What are the ways for that? So there are two ways, like we can do it via traditional photogrammetry, like it's the traditional approach. So this is also like the structure from motion. So the idea of this traditional method is structure from motion. So the classical approach matches feature points across images to triangulate a 3D mesh. So what it means, I'll tell you. So now we are learning how we can do novel view synthesis. So now idea is very clear that I will be provided with image along with the camera pose, that okay, this image was took from this angle, this image was took from this angle, this image was took from this angle. So this information I will be having. Now from this information, how I will be able to do synthesize novel images using the traditional approach. So in traditional approach, what we used to do is, first we used to do the feature detection. So whatever sample we have, images and the pose angle, we used to detect the feature. And in feature detection, we used to focus on like the corners, edges, and then we used to do the feature matching. What we do, like whatever input we have from every image, we used to detect the features. Then we try to connect the dots, that we call it feature matching. So now we try to match the feature, that okay, for this image the border is here, For this image, the border is here, and this is the pose angle. So a sort of, we are trying to recreate the scene from the information of in the image and from the pose angle. Then we used to do structure from motion. So after feature matching, then what we used to do is that with whatever insights we have derived, we used to identify the structure from motion. So now we will take different camera poses together, and we'll try to recreate a structure based on the features. Like, I'll join this border, this edge, this edge, this edge. Oh, this is a triangle I'll get, like that. Like a very basic idea I'm giving. So see, this is not like we will go very deep. It is like to get an idea. And if you're interested, you can dig very deep, because it's very interesting. Like novel view synthesis is very interesting. You can go very deep and you can actually do it. Then we have multi-view stereo. Okay, then after structure from motion, we will have something called as multi-view stereo. Then with that multi-view stereo, we will have mesh reconstruction. We'll reconstruct the mesh, and on top of the mesh, we will add the texture. So here, what has happened, I'll tell you. Like the main thing we should focus here is, see, whatever input we had from every image, we did the feature detection, then we did the feature mapping. Now that feature mapping and then the structure from motion. So whatever structure we got, it is highly discrete in nature, because it does not contain, it is not continuous, it is discrete. So many missing information is there. And then from multi-view stereo, still it is discrete. As you can see, many missing gaps is there. Then we will just connect the points. So to fill the gap, we are connecting the points with the straight line. So we will get a mesh. From discrete structure, we were able to generate a continuous surface via mesh. So all these discrete points, we just connected it with lines. We got a mesh. Then on top of that, we applied the texture. And here, lightning plays a very important role, because whatever information we have from the input, that we will make use of to apply the texture. And in this way, all the unknowns we were able to build, because we had discrete information. But with the mesh, like I connected it with straight line, I was able to generate a continuous surface, and that too in 3D. So I was able to generate a continuous 3D realistic experience from 2D. And the beauty of this technique is that it also contains realistic experiences in unknown poses, like the angles from where we haven't captured the images. That angle also it covers. We can see that, okay, from this angle, how this object will look. So the advantages of the classical method is, it is physically interpretable geometry, and the pipeline is very deterministic in nature, because like we are doing a fixed set of tasks. So once you make this pipeline, very easily you can do it. So fixed set of tasks we are doing. So it's like a deterministic pipeline we are following. Now the limitations with it is, so we need some good amount of images. So the more the images we will have in input, more realistic the output will be. Okay, so the challenges, we already saw that it struggles with reflective or textureless surfaces, and poor performance with sparse input. Because if the input, sparse input means if it is spread, if the input is spread, then the performance will be poor. So that is the traditional or the classical approach of novel view synthesis. Okay, now we'll discuss something like AI driven NVS approaches. So novel view synthesis using AI. So in AI, what happens is that like input, so we will have the same input, like images along with the camera poses, viewpoints. Now what we will do is that we will train a neural network. So there is a technique called neural radiance fields. So in neural radiance fields, what we do is that we train a small neural network. Like we'll take a small neural network and we train it, and it will be a supervised training. Supervised. So in supervised learning, uh, we train the model that okay, these are the images, these are the viewpoints. So and then it will learn that okay, the image from this angle it looks like this, from this angle it looks like this, from this angle it looks like this. So it will learn the neural network. So we train the neural network to represent the scene as a cloud of density and color. So how we train that we will see very soon. We will come to that how exactly the training will be done to get an idea. But like the idea is that okay, input I gave, there is a neural network, we trained it, how we trained it, that we'll discuss very soon. Then it will generate output. So we will get learned scene representation. It can be a implicit function or voxel grid, and output is the photorealistic novel view. Okay. Now let us see how we will be like neural radiance field. If I talk about here, I train a small neural network. How I train? To render a pixel, we shoot a ray into the cloud and ask the network how much light is reflected here. So the idea is very clear. See, once again, I'll tell you, in neural network method, what we do is that we need lots of data. So I have lots of images along with the viewpoints. I give it to the neural network. Neural network will learn that, okay, from this angle, the images look like this. And what it will learn is, it will learn the cloud of density and color. Like image, the distribution of pixels and the color, the intensity, like in that distribution, the color intensity. So the neural network, for every image, it will learn that okay, from this angle, this is the cloud density, wherein the distribution of pixels and the color. From this angle, this is the cloud of density and color. From this angle, this is the cloud of density. So whatever angles we have covered, so from different angles, it will learn the cloud of density and color. Now what will happen is that the idea is that now let us suppose I want to render a image or a 3D scene in a completely new angle. So what I'll do is that I'll shoot a ray into the cloud and ask the network, I'll query the network that okay, for this coordinate, and the angle is this. Shooting the ray means I'll tell the neural network that okay, this is the camera angle, and for this particular coordinate, what will the pixel look like, the 3D pixel will look like. That is the query I will give to the neural network, and it will tell me okay, the pixel density should be this, pixel intensity, color intensity. So in this way, what I'll do is that whatever the camera angle is, I have to send many queries. Like for every point, I have to send a query, every coordinate XYZ, and it will give me the information. And using that, I'll create a photorealistic 3D scene. And the best part of this is it will cover unknown regions as well, which we have never seen before. It is been synthesized. So this is like the approach of novel view synthesis. It's a modern method. Now the advantage of it. Okay, so before that, so now it's very clear that okay, input we have the images and the camera poses. Then we have a neural network, which is the learned scene representation. And then output will be the photorealistic novel view. Now, neural radiance fields, the advantage is that photorealistic handling of light, transparency, and reflection. So, uh, as compared to classical method, like neural radiance field method, it is very good in learning light, transparency, and reflections, because here we are dealing with the pixel intensity. So it can very easily learn light, transparency, and reflection, and it will take care of that while generating the novel images. And the cons is it is extremely slow to render. Why it is slow? Because we have to query neural networks a lot. For every coordinate, we have to query it. So originally it took minutes per frame. So in order to render a frame, it may take minutes. So it can be like very time consuming. Now, what are the key advantages? It works with fewer images, captures fine details, handles complex lighting, and produces photorealistic results. So this is like a very important advantage of AI driven novel view synthesis approach. So if we like compare like the it is like the classical approach, and these two are like AI driven approach. We will discuss AI driven approach in some great detail, and this lecture is about Gaussian splatting only, so that also we'll discuss very soon. So in AI approach we have neural radiance fields and Gaussian splatting. So if we just compare these two approaches, so the idea is that the output of classical approach is textured mesh. The output of neural radiance field is neural weights, because here we are training a neural network. And in Gaussian splatting, the output will be point clouds, and these are not like a spherical points, but these are like ellipsoid, ellipse in 3D. We call it splats. So we have 3D like ellipsoid point cloud. So that will be the output of Gaussian splatting. Rendering speed for classical it is fast, for neural radiance field it is slow. We know why it's slow. And Gaussian splatting to real time, it's extremely fast. We can do the real time rendering, and that is like very interesting. Okay, it cannot handle reflections. It's poor in handling reflections, the classical approach. Neural radiance field is excellent in handling reflection, and Gaussian splatting is excellent in handling reflection. The best use case for classical neural novel view synthesis is surveying and maps, because their texture and all will not play that much role, the lightning reflections and all. For offline CGI, like computer graphic interface or neural radiance fields can be a best use case. And if we want real time, like in VR and games, then Gaussian splatting we can go for.